Hello, good evening, greetings, Internet from a rainy Southampton. So this event is part of the Southampton Science and Engineering Festival, organized by the Public Engagement with Research Unit at the University of Southampton, and it's running from the 11th of March to the 20th of March, as you can see on the slide. If you want to comment on social media about today's event, please use the official festival hashtag SOTSEF. Okay. Right, so let's start today's talk. I'm Jacek Brodzki. I'm a professor of pure mathematics here at the University of Southampton. And the topic of my talk is, well, is the Earth flat? From geometry to the modern world. I really would like to start by saying that I don't really consider this a point of debate. For me, the issue has been settled, as you will see, a very long time ago. But there is quite a lot that we can learn from this, so let me explain. The talk will have to do with a branch of mathematics called geometria in Greek, which is geometry in English. And when you unpack it quite literally, it means measuring the world. That's what it is, that's what geometry is, and that's what it's been designed for. Geometry has been with humanity throughout its history. There are traces of geometry and geometric thinking in all preserved historic records. So we can safely assume that this way of understanding the world around us has been contemporary with humanity throughout its history. When I say geometry, you may have recollections of various facts that you learned at school or various other times in your life. And one of them is a very famous result, which we know has been handed down to us under the name of Pythagoras, who lived in a Greek colony about in the 6th century before Common Era. And there are numerous statements, numerous equivalent statements of this result, one of which you can see on this slide, that if you have a right-angled triangle, the square on the side opposite the right angle, which is blue in my slide, equals the sum of the squares containing the right angle. So that was that's a modern rephrasing of a statement of Pythagoras' theorem that we know from Euclid's Elements, which was the first almanac of geometric knowledge up until that point. You will see that there is no a squared plus b squared equals c squared in this formulation, simply because that notation is a much more modern discovery, and we needed the contributions from the Arab mathematicians of the Middle Ages to help us actually discover algebra and then discover modern notation for that. Just one point before we move on, note that Pythagoras says that this square on the side opposite the right angle equals the sum of the squares containing the right angle. Okay, the Greeks, the ancients meant this quite literally. To them, Pythagoras' theorem was as much about calculation as it is about geometry. But as I said, there are traces of geometric thinking in all artifacts that we have discovered. So for example, here you see a very famous clay tablet, which is Babylonian, and it precedes Pythagoras by more than 1,000 years. And on it, if you know how to decipher this particular cuneiform writing, you see 3 numbers that together give you an example that form a Pythagorean triple, which means that they satisfy the equation that we associate with Pythagoras. As you can imagine, as you can see, these numbers are large enough, so we can be quite certain that they have not been discovered by accident, that the Babylonians knew how to create numbers of that type. One reason to do that, and clearly this probably goes beyond geometry of the immediate neighborhood, of the vicinity of where they lived, and this has to do with calculation. Many of these formulae, many of these discoveries were simply shorthands for computation. One way to use a formula like this is that if you come across a number like 4,825 and you want to square it, well, perhaps you've come across, perhaps this is part of Pythagorean triple, so you would have known these two squares, and adding is always easier than multiplication. As I said, the issue of whether the Earth is flat has been settled a long time ago. The ancients knew that that humanity lives on the surface of a gigantic ball, and that has been known throughout essentially ancient history. But here is a very beautiful example of a geometer and polymath, Eratosthenes, who lived in about 200 years before Common Era. So he was a librarian in the Library of Alexandria, and he was we would call now a mathematician. He was a geometer. He was a polymath. He knew a lot of what is to be known about the knowledge of the times. And one of the discoveries that he made was that he lived in Alexandria, but that he heard from travelers that in Sienne, which is now called Aswan, and it's a city in Egypt, there's the people have observed the phenomenon that on a particular day, the spring equinox, sun's rays fall down to the bottom of deep wells. Aswan is slightly north of the Tropic of Capricorn, and again, people knew what tropics were. So Eratosthenes used, well, here you can see an obelisk in the Library of Alexandria, but you can use any kind of vertical object whose length you know. So he used that to measure the angle that sun's rays make with the vertical at that point on spring's equinox. So he discovered that the angle between the vertical where he was in Alexandria and the sun's rays is about 7.2 degrees of arc. So if you know, so that's about 1/50th of the full circle. So he knows if you knew the distance from where he was in Alexandria to that well in Aswan, then you could calculate from there the length of the meridian. But of course, measuring a distance of that scale is never easy, and particularly back then, there were no established units of measurement, if you like. The only way to do it is, for instance, to estimate how long a caravan of camels would need to travel from one place to another, and use that to try and estimate these distances. That you will immediately appreciate is not particularly easy to do, because camels will walk at different speeds. Like your camels may be faster than my camels, and so the legend has it that he actually hired some surveyors to walk this distance and count the number of even steps that they made. From there, he made the estimate that the length of the meridian through Alexandria and Aswan, they are not exactly on one meridian, but that was close enough, equals to 252,000 stadia. So if you want to translate this to modern units, then you need to ask yourself, so how big is a stadium? And of course, we don't know precisely what length of a stadium Eratosthenes meant. So our modern estimates were based on various sources from antiquity, that's the lower estimate for his result was 39,060 kilometers, and an upper estimate was 40,320 kilometers. Essentially, it's the definition of kilometer that the length of a standard meridian is 40,000 kilometers. So he was very, very close. The lower limit is about 2% off. So you have to you have to agree that this is just a tremendously precise estimate to make. And as you can see, it shows confidence that people knew what shape the world had. But one thing that this immediately comes to that you notice in this beautiful estimate is that to do this, to calculate the shape, the size of the Earth, you needed this astronomical phenomenon. You need the sun to be there. You needed to provide the shadows. You needed to create something that you can compute. So when you ask the question, is the Earth flat? It's important to ask, what exactly do you mean by flat? When you think about this for a moment, flat is one of those annoying words that, well, if you try to define it, we very quickly follow some circular reasoning because flat, so what is flat? Flat is something that isn't curved. Well, so what is curved? Well, curved is something that isn't flat. So we're not making progress. We can show, we can demonstrate how to make flat surfaces, but the purpose of this talk is to derive some more intrinsic ways of measuring. So my story about Eratosthenes shows that if you have some way of getting off the planet, then you can actually convince yourself that the Earth is a beautiful globe, quite fragile one at that, and you can of course measure its size. So if you like a million miles away, and you have access to NASA's Deep Space Climate Observatory, you can see beautiful pictures like this. So this is the Earth from the side of the Americas, and here it is from the side of Africa. So it has two sides, so it rotates. As you come closer, for instance, somebody bought you a ticket to go to the ISS, it will look a little bit like that. So you still see curvature, and this is probably slightly less pronounced than what you've seen before. A lower Earth orbit, you have beautiful pictures like this one. And if you come closer still, so if you're at the top of a tall building, then it becomes debatable, right? Do we see curvatures? Are these artifacts? Is this curvature real, or is this an artifact of the way I've taken the picture? And if you come closer still, so this is what my garden looks like from about a meter high. I don't see any curvature anymore. It's just a flat piece of grass. And from ground level, the Earth looks like this near where I live. So this question, how do I know that the Earth is flat, is quite important. And this is going to be a major part of the first section of this talk. So when you think about a flat surface, your imagination might create a picture like this. What you see here is something that we would call a flat surface. So I have a rectangle which is divided into a square grid, and this grid is made of parallel lines. I said two words here that require explanation. First, a line. What is a line? What is a straight line in particular? That's something that the ancients never defined. In Euclid's geometry, a line was something that was self-evident, that a straight line, you knew what it was. It somehow, he never gave us a definition of that. Now, parallel lines are lines, and this is an ingenious extension and shows that they had great power of abstraction. So parallel lines are ones that if you extend them indefinitely, they never meet. That's really something quite important. And of this, the ancients knew how to, given a line, how to create a family of lines parallel to it at equal distances. And that is because one of the axioms of Euclidean geometry is that if you have a line and a point not on it, there is a unique line parallel to the one you started with that goes through that point. After much effort, it was discovered that this axiom is actually independent of the rest of Euclid's axioms. So this is not something that's, if you like, fixed forever. And I will show you in a moment what why this is relevant. But for now, it's a central part of Euclidean geometry that if you have a line and a point not on the line, you can draw a line parallel to it going through a point. Why this is important? A lot of elementary geometry rests on statements like that. And one of them would be something that I'm sure everyone listening to this talk knows only too well. And it's probably so unexciting that you're now beginning to think, why have I tuned in to listen to someone tell me that the sum of the internal angles in a triangle is exactly 180 degrees? But please bear with me. It will get exciting very shortly. How do we know that this is true, first of all? Using what I just told you about parallel lines and taking vertex as a point not on the line through the base, I can draw a parallel line through it. Extending the size of my triangle, I get this beautiful picture. And now, something that I'm sure many of you will recognize from elementary geometry, I can now compare angles. We have beautiful statements about comparing angles created by lines intersecting parallel lines. So you know that this angle at the bottom right of my triangle is the same as the angle at the top here. The same goes from about the angle at the bottom left. It equals the other angle on the right. And of course, the lines at the top vertex of my triangle are the same. Okay? So I've arranged the three internal angles so that they match together to form one semicircle. And we know that the angle associated with this semicircle is 180 degrees or pi. Okay, so this is how we know that the sum of the internal angles in the triangle is 180 degrees. Okay, but we've agreed that we live on the surface of a ball. So is any of what I just said actually true? So one immediate question that comes to mind, so what is a line? What is a straight line on the surface of the sphere? So it's clear that the Euclidean straight lines no longer live on our sphere, right? You can't really have a straight line on this sphere. It will poke through it, and that's not what we do in our everyday experience. We travel along curves that sit on the surface of our beautiful ball. So we need to understand what would be a good analog of a straight line in our situation. So indeed, what is a straight line? I told you that Euclid never defined it, and we had to wait until Descartes in the 15th century when he created coordinate geometry, where a straight line was a particular curve satisfying a particular equation. But there is a different way to look at it. If you want to walk from one point to another, there would typically be very many ways to do it. In fact, infinitely many different ways to do it. Is there something special about the Euclidean line connecting the 2 points that you have chosen? So let's introduce a new word here. A geodesic between 2 points in your space is the shortest path that connects them. Okay, and an awful lot of mathematical discovery has gone into proving the fact that in the plane, geodesics are straight lines. Okay, so the straight lines that we know are in fact in the Euclidean plane are the shortest lines between any 2 points. If you say to me at this point that you knew that all along, I would disagree. It's an awful lot of beautiful mathematics that's required to actually prove this. But what about the sphere? Okay, we don't have straight lines, but we have geodesics. We have shortest lines between points. And on the sphere, geodesics are great circles. So what is a great circle? Imagine that you have the sphere and you slice through it using a plane. And if your plane goes through the center of the sphere, the intersection of the plane with the sphere is a great circle. So great circles are ones that go through the poles of your sphere. So you have a North Pole up here and a South Pole down there. So all those meridians that you see in my picture are great circles. There are other circles on the sphere, the horizontal ones that you see, but these ones are not great circles except the equator. The equator is a great circle, which is among the horizontal circles. So let's agree that from now on, geodesics, shortest lines on our sphere, are arcs of great circles. If you fly anywhere, your plane will follow a line of an arc of a great circle. If you navigate on a ship, your ship will follow an arc of a great circle. So these have been with us since antiquity, since people started navigating. This is how you travel on the sphere. Okay, but I just told you that these great circles all go through one pole here and another on the other side. So they all intersect. And you discover immediately that there are no parallel geodesics on the sphere. So that's very, very different to what we've seen in the Euclidean plane. And so let's see if we can actually discover consequences of this amazing fact. Well, so let's look at triangles. Just a moment ago, you were falling asleep because I was trying to excite you about the fact that the sum of the internal angles in the triangle in the plane is 180 degrees. So let's draw a triangle on the sphere. Triangles make perfect sense. You can take 3 points on the sphere and you can connect them using shortest lines. We now know what that means. We know what geodesics are. There will be arcs of great circle. So if you take a really big triangle, so that one vertex is at one of the poles and you have 2 vertices on the equator, for example, your triangle can have 3 right angles. Okay, this doesn't happen in the plane. We know that that's impossible, but on the sphere, hey, we can have a triangle with more than whose internal angles add to more than 180 degrees. So Pythagoras' theorem, for example, does not hold because here is a right triangle. In fact, it's very right because all its angles are right. Okay, I've arranged it so that it's isosceles, which means that all its sides have the same length. Call it A. So Pythagoras' theorem in this case would say that A is supposed to equal A squared pi, A squared is supposed to be equal to A squared by plus A squared. But that is clearly nonsense. So Pythagoras' theorem, ladies and gentlemen, does not hold on the surface of the sphere. I already told you that my triangle has 3 right angles. So the sum of the internal angles in this particular triangle is 270 degrees. And you can see that it can be more. You can imagine that I move one of those sides to open up the angle at the top. And it can be as big as you want all the way up to 180 degrees. So in an answer to our question, how do we know that the Earth is not flat? We are discovering geometric facts which are very different when we try to apply them to objects that live on the surface of the sphere to when we lived in the Euclidean plane. And in fact, this is such a good discovery that it deserves a name. Let's call it measure of curvature. Let's imagine that you can draw a triangle in your world, taking 3 vertices and connecting them by lines that you will declare to be geodesics in the geometry that you are constructing. So these will be the straight lines in the Euclidean plane. There will be arcs of the great circle on the sphere, right? So you can build triangles, compute the sum of the internal angles in a triangle, and take pi away from it. Okay, so that's delta. The name of that difference will be delta. All right, so we have the following 3 possibilities. If delta is positive, we are in a positively curved world. So the first surface of our sphere will be a positively curved world. And now this delta tells us that that's where we live. If delta equals exactly 0, so the sum of the internal angles in a triangle is exactly pi, is exactly 180 degrees, this is when our world is flat. So now we have an answer to our question. What do we mean by flat? Flat means one of the answers now to this question is that flat means that delta equals 0. You can ask if there are worlds where delta can be less than 0, which we would call negatively curved. And I'm so glad you asked, because that's the beginning of another wonderful story of hyperbolic space. So hyperbolic space, in this model created by Henri Poincaré, the great French mathematician who lived between the 19th and the 20th century. This is a world whose model is this disk that you see, and the lines in that world are exactly the lines that you see here. So they allowed straight lines through the center of this disk, together with arcs of circles that meet the boundary circle at right angles. And these are the geodesics in my geometry. These are the lines I'm allowing. So here's an example of a triangle. Okay, it has one vertex here, one vertex in the center, one on the boundary. But look what happens. Because all these circles touching the boundary, they all meet the boundary at right angles. The angle at which they meet is exactly 0. All right. So this angle, the angle of my triangle at this vertex is 0. So no matter what these angles are, the sum together with the 0 angle will be less than 180 degrees. It gets better. You can have a triangle with 3 vertices on my boundary vertex. So here you have a triangle whose internal angles are all 0. Okay, so the sum of these internal angles will be 0. So now you see that there are possibilities of having various geometries, and we can distinguish how curved they are, whether they're positively curved, flat, or negatively curved, using our newly discovered measure. There is more that we can say. So let's just take a brief detour and talk about Archimedes, who was one of the greatest mathematicians of antiquity and probably one of the greatest mathematicians ever. One of his many discoveries, he was interested in measuring the circle. And what he meant by that is that he said with confidence that for every circle, whatever, the ratio of the circumference to the diameter is constant, and it's a number he called pi, or we call pi, and he provided a first estimate for how big that number is. It's 3.141, and that was an amazing discovery. It took more than 2,000 years to actually make it better than what Archimedes did back then. Okay, so how about our spherical geometry then? So let's draw some circles on the sphere which are not great circles. So if we take a small circle, for instance, surrounding the pole, then this little piece of our planet will be essentially flat. That's like a piece of my garden I showed you. That's essentially flat. So here, when we take the circumference of the diameter, this ratio is more or less pi. But take some big circle, like take our circle to be the equator. what is the diameter? The diameter has to be an arc of a great circle. So for example, this will be a line that goes through the North Pole. But on the sphere, this is like half the circle and the equator is the full circle. So this circumference divided by the diameter is 2. That's very far from pi. So you see, on the sphere, Archimedes' discovery would not hold. The, the ratio of the circumference to the diameter is no longer constant. It depends on how big a circle actually is. And I will leave it to you to study how that works in hyperbolic geometry. But let's speed up our discussion of the story of geometry. So two great mathematicians, Carl Friedrich Gauss and Bernhard Riemann, Gauss, who lived at the end of the 18th century, at the beginning of the 19th century, and Riemann, who lived in the 19th century, they took these ideas together with others like Bolyai and Lobachevsky and Sofia Kovalevskaya and others to create a geometry of curved spaces, something that we now know as Riemannian geometry. It's the geometry of spaces which are not flat. And this line of inquiry continued to this day, and one of the great contributors to the really modern version of that was Maryam Mirzakhani, the Iranian mathematician who sadly died very young, at the age of 40, and she made astounding discoveries, astounding contributions to this area, and that gained her the Fields Medal, the highest honor in mathematics, in 2014. The beginnings of that modern story were humble and took root in many practical problems. For example, now that we know how to measure things on the surface of the planet, you might know how big is your country. If you are a duke or a king or an emperor, you might want to know just how much land you rule over. To answer this question, people like Gauss and surveyors before him developed something that is now called triangulation. Triangulation means divide the land you're interested in into triangles. Why? Because if you want to compute the area of anything, you need to start with shapes whose area you can calculate. And this was known to ancient Greeks, and people like Gauss and others have developed this very practical way of approximating the shape you want to understand by simple shapes, in this case, triangles. And Gauss, the great Gauss, was involved in many aspects of this study. He actually traveled on foot, on horseback, measuring these large triangles. And in fact, if you walk anywhere, it's easy to come across triangulation markers. They still exist to this day, and you can look them up. And at this, we pass from the study of distances, study of triangles, to the study of shape. This is something called topology. And it deals with understanding complex shapes that may not be so easily describable through something simpler. So for topology, if you take this polyhedron on the left and inflate it, you get the ball that you see on the right. At the beginning, at the foundations of this are Gauss's discoveries that complex shapes can be built out of simple ones. And topology takes this very, very seriously. And let me now demonstrate what this means and how that relates to modern world and modern data analysis. And for that, we need to talk about lemurs. So lemurs, as I'm sure you know, are primates. They live on the island of Madagascar. That's the only place they survived. And there are a great many of them. The variety of that subfamily of primates is quite remarkable. And you might want to know just how they related to one another. So here is an evolutionary tree of a family of lemurs, and you might want to know how they're related. And for that, you might want to take something that they all share, for instance, a particular tooth, and ask, are they similar or are they different? Would I know that this genus of lemurs is related to this one, or maybe this one, or maybe how do I know that these particular lemurs are closer to this, but not to that? So what you see here are teeth, they're molars, they're on the side of the jaw, with markers put in there by experts to denote points which play the same role on those particular shapes. And then you ask, can I use the geometry that I've learned by looking at what Archimedes has done to actually make sense of that? And the answer is yes. You can use what we have done to understand curved spaces to create, if you like, um, coordinate systems on these strange looking shapes, right? There is quite a lot of beautiful discoveries, including taking CT scans of those shapes, rendering them like you would in a cartoon movie, and then creating this piece of mathematics that will give you shapes of, that will divide your complex shape into pieces whose area you will know. And then comparing those, you see, using similar ideas to what we've discussed in the first part of this talk, you can actually develop measures of similarity and dissimilarity between these shapes. So you can then create a notion of distance, if you like. Is this particular shape similar to the one I show next to it, or maybe it's more similar to another one? And here is a particular practical problem from data analysis. So let's imagine that we've collected enough of these objects from 5 different species of lemurs. So, okay, the rows here show 5 different species, and the teeth are from the same part of the jaw. Can we actually use these ideas of curved spaces to compare them? And the answer is yes. This is one of the projects that we did here in Southampton. And those 5 species of lemurs can be split into 3 groups. And those 3 groups have those beautiful names. They're called folivorous, frugivorous, and insectivorous. And this means the first group eats leaves, the other eats fruits, and the third eats insects. So geometry, those geometric ideas, when applied to the shapes of teeth, will detect that the shape of your tooth depends on what you like to eat. Okay, so this was done without any knowledge of the anatomy of these wonderful animals. But let me tell you some in the last few minutes of this talk. Let me just introduce other fantastic, remarkable ideas, the topology, which developed along these ideas all the way from Archimedes to the modern time. So let me give you some medical applications now. So in the 1970s, in 1977, 2 Stanford scientists, Raven and Miller, decided that they want to investigate the precise relationship between diabetes type 1 and diabetes type 2. They collected data, which they analyzed using cutting edge methods at the time. And in the abstract of the report, they say that when they rendered, then when they've done analysis that allowed them to render the data in 3 dimensions, they say that when this was done, the picture of their data set was that of a boomerang with 2 wings and a fat middle. You don't expect to see words like this in the report of a cutting edge project from a world-leading university. And what they meant by this, and this is an artist's impression of what they meant. So this is a boomerang, these 2 floppy ears is the boomerang they're referring to, and this is the fat middle. But here's the amazing thing. We can't describe this shape beyond what they said in the abstract, but the fat middle consists of controls. The controls are participants in any medical study that do not have the the disease that you want to understand. They do not have that. So if you remove the middle, these are the healthy people without diabetes. One of those floppy ears is diabetes type 1, and the other is diabetes type 2. So amazingly, they were able to show immediately that type 1, diabetes type 1, is disjoint from diabetes type 2. And that was a tremendous discovery. And that was one of the first examples of a topological thinking that led to new methods. This is a modern rendering of the same data set where you still have one ear, the other ear, and the fat middle consisting of controls. And a tremendous extension of these studies, topological methods applied to this data set, give you a further finer classification of diabetes of type 2. There are 3 distinct subtypes with their own medical and biological medical characteristics. So knowing something like this is priceless because patients in these 3 different groups can respond very differently to the treatments that you would like to apply to them. And this is one of the breakthrough results from just over 10 years ago that started applications of topology to data analysis, which is now known as topological data analysis. This very unassuming picture shows a topological representation of patients with breast cancer. And there are various confusing sounding names here, but one of the huge discoveries is that separated from the rest through sparse data, so the connection between the group this arrow is pointing at and the rest is very, very small. So this is essentially a separate cluster of patients. And when experts looked at the patients and in this group, they realized that they discovered a new subclass of breast cancer where patients exhibit 100% survival and no metastasis, so that the cancer does not spread anywhere else in the body. So I hope you see the power of these methods that we can trace all the way back to ancient prehistory of humanity, that now using the topological ideas that I described to you, using the geometry that we have introduced, we can now say with certainty that patients represented by the dots in this part of my data set, that those patients have a tremendously good prognostic if they're unlucky enough to get breast cancer, which in fact is what killed Mariam Mizahani. Yes. So this is the end of my talk. I tried to demonstrate that there is this uninterrupted flow of ideas through the history of mathematics that goes as far back as we can trace it. That mathematics provides the structure and methods to make sense of the complexities of our world. And mathematical discoveries, mathematical truths never go out of fashion. They never grow old. They never cease to be relevant. Okay? And that kind of certainty is quite positive in our fast changing world. And with this, I will stop. If you have any questions, I would invite you to post them either through the chat or any other means. So thank you. Okay, so I see a question in the comments here from Tobias. Do we think maths will evolve further than it already has? Most definitely, yes. We are nowhere near exhausting the problems that humanity is facing. There are new connections between mathematics and other sciences. The discoveries I told you were inaccessible. The medical discoveries I showed you were inaccessible a short while ago. And now we have we have topology, which is regarded as a purist of the pure mathematics, very, very theoretical, contributing directly to that. So there is no doubt in my mind that we will see further breakthroughs in mathematics. Yeah, that's a very good point. I don't think mathematics will survive all of us, I think. So Bethany asks, are there any other ways that geometry can evolve the way we live? It definitely provides insights into the shape and structure of our world. That's definitely true. I'm hoping that through the discoveries to which mathematics is contributing into the data-intensive science, that we will learn about us, about the planet, about the complex problems of the day. I'm sure that, um, in fact, I'm involved in projects that attempt to make sense of climate data, that attempts to make sense of how we communicate and so on. So most definitely, yes, there are results that can be translated back into the areas where they came from. And yes, so the answer is yes, I'm quite sure that not just geometry, but general mathematical thinking can most definitely influence how we live and how we communicate. Yeah, and thank you for your question, Tobias and Bethany. Yes, yes, it's quite remarkable. It's very, very recent that mathematics is applicable to really difficult problems in medicine, biology, and so on. I think a lot of this is thanks to the tremendous progress that has been made in these sciences. So that's quite remarkable. We now know that the mechanisms controlling living organisms and the way they interact are so complex that you need a new kind of mathematics, um, to deal with that. In that context, I encourage you to look up the beautiful videos on YouTube that explain, for instance, how the anti-COVID vaccines work. It's just amazing how much we know. So we have another question from Bethany. Do you think that artificial intelligence will have any competition against traditional mathematical techniques? Now that's a very astute, very deep question. I mean, can a mathematical discovery be automated? There was one of the questions that um, um, people pondered for over 100 years. It goes all the way back to Hilbert, and Alan Turing made tremendous contributions to that. The great Alan Turing, one of the greatest mathematicians and computer scientists in this country, he demonstrated that there are numbers that cannot be accessed by computer. So the answer is twofold. On the one hand, mathematics needs humans. You cannot hope to discover all of mathematics using just pure computing power. On the other hand, does artificial intelligence have place in this? And the answer is most definitely yes. We are now faced with problems so complex that are described with data so manifold that to make sense of that data, we need seriously powerful computational techniques, and artificial intelligence is one of those technologies. So the answer is here, yes. However, humans need to understand. So if a computer knows the answer to a question, but you have no idea what that answer is, like it's 42, then it has, as has been beautifully demonstrated by Douglas Adams all the way back in the Hitchhiker's Guide to the Galaxy, humans will not be satisfied with that. They will need to have our own human understanding. So artificial intelligence will be great, or is great for creating new insights, but we will need mathematics to actually make sense of that. We will need something that humans can understand. Otherwise, the machines will just take over and we will be obsolete. Thank you all. Yes, thank you. Do you have any further questions? I'm really happy to stay here and talk. There is plenty of time. I do recognize that this is a fairly rigid format, typing questions and so on. So let's just wait a few more minutes to see if there are any more questions. So Sylvie asks, will quantum supercomputers affect the speed and depth of mathematical discoveries? So yes, the answer is yes. So quantum computers will create new methods that will allow us to blitz through calculations at tremendous speeds compared to what we have here. On the other hand, there are problems, there are theorems in computer science, there are theorems in mathematics that measure the complexity of problems, and some of them will simply grow faster than our computing power. So there is always a tug of war that, yes, we can compute more quickly, so we can compute more examples, but unless our computer is the size of the universe, at some point it may run out of puff, even if it's so powerful as a quantum supercomputer. So on the one hand, yes, we will be able, for instance, if you want to predict climate in real time, so you essentially want to be able to know what the air on Earth is doing at any given moment, that means you need to track something at the order of 10 to the power 23 of air molecules if you want to know what they're doing, if you want to understand air and wind at molecular level. So there's a tremendous amount of computation power that's required if you want to do this. So if you have really powerful quantum computers, then yes, the size of the systems you can model in real time will increase tremendously compared to what we can do now. So yeah. And again, to make sense of that, you will need mathematics to again grow many levels in sophistication and difficulty to match this. So yeah. So I hope that answers the question. Yeah, thank you for your question. So Tobias makes another good point. The human side of mathematics is always going to be challenging. How can we make sure that we educate the younger generations to love it and understand its powerful value? Well, mathematics and mathematical thinking has been attractive to humans always. So there seems to be part of humanity that will always respond very well to this kind of thinking. I think the best way that we can excite people about mathematics and to keep showing how relevant it is, that simply by sitting down and thinking a little, we can access and solve really complex problems. And that's unusual. You see, this is this. So I think just showing people um, what amazing stuff mathematics can do, how varied it is, how beautiful it is, I think is the way to do it. And there are wonderful mathematical investigations accessible at essentially all levels of mathematical education, starting in very early years at school. And those are really significant, interesting, non-trivial studies that um, can be shown to students. So that's the only way I know how to do it, is just to tell people something which is beautiful, something that's relevant, and something exciting, which I hope my talk has managed to do it in at least some tiny part. So Emily asks, are there ways in which mathematics can be used to predict and mitigate our climate crisis? The answer is yes. There are many ways. Yes, most definitely. Mathematics can help with understanding uh, the climate, can understand sustainability problems, can understand how humans will live in that new, fast-changing world. However, there is an important point, that whatever conclusions we arrive at need to be presented to the wider humanity in a way that's accessible and in a way that humans are willing to accept. The current pandemic crisis illustrates even more vividly how difficult it is to get across and make people accept um, some scientific discoveries. So that's a challenge, but most definitely, yes, I think, Emily, you're right. You're absolutely right. Mathematics can contribute greatly and is contributing greatly already to all this. Yeah. Okay. It seems that we don't have any more questions, so I propose that we stop here. It's been fun for me. It's been an honor and pleasure to be able to address you. I do hope that you enjoyed the talk, and there will be many more events in this festival. So first of all, before you go, we'd be really, really, really grateful if you could please tell us what you thought about today's session. You can do this by taking part in this short anonymous survey, and you can access it either by scanning this alien-looking QR code or by simply typing the link that you see at the bottom of the slide. And if you could do this, we would really, really appreciate this, because we are passionate about this festival and we would like to make it as better, as good as it can be. And yes, so finally, as I mentioned earlier, this particular event is part of Southampton Science and Engineering Festival, which we called SOTSEF. And this is taking place from 11th until the 20th of March. So to know more about the festival, please explore the interactive resources and join other live events. there is a link at the bottom of the screen. I hope it's memorable enough. And thank you very much for being here. Good night.